Questions about anything? Last time or anything? Well, it felt like a good time to do something special. I can give you a complete proof of the fundamental theorem of algebra using sort of a minimum of analysis, because many of the things we've been working on over the semester apply to this situation, and we can just use facts we know, sort of in a clever combination, but still it's quite straightforward using facts we know. And so the famous fundamental theorem of algebra, complex polynomials I've written there, where the a's can be in C. And the fact is, if that polynomial has degree 1 or more, then it's guaranteed to have a root in the complex plane. And that's fascinating because even if those coefficients are real, it's very possible to come up with real polynomials that don't have any real roots. The classic example is, for example, x squared plus 1. And whenever you have a complex root, you can factor out that complex root. So this factors over the complex numbers as z minus I times z plus I. So it's a corollary that when you get a root, you can factor out. So a corollary of the fundamental theorem of algebra is polynomials factor. So that polynomial of degree n would be a z minus root 1 to the multiplicity 1 times z minus root 2 to the multiplicity. Whenever you have a root, you can divide out a z minus that root, and you might be able to do it more than once if it has multiplicity. So there are a bunch of roots. Let's call the last one r sub j mj. And those m's add up to the degree. Summation I equals 1 to j of the mi's is equal to the degree of the polynomial. So to really understand polynomials with real coefficients, you've got to go into the complex numbers. That was discovered way back when people started solving the quadratic equation. When you complete the square and write the quadratic formula, you realize, oh my gosh, I'm going to need square roots of negative numbers. And so that's how the complex numbers were invented. And it's a lucky thing that adding that one complex number, I, gives you all you need to solve every polynomial equation. Every polynomial has roots. So that factoring business just comes from the Euclidean algorithm you learned in high school. I won't go over that. But the key fact that I'm going to use here today is that complex polynomials are complex differentiable. And complex differentiable functions are really interesting and come up everywhere in science and math. They're called analytic functions. If they're a complex differentiable on an open set, they're called analytic. Okay, so let me tell you what complex differentiable means. A definition. A complex function of a complex variable, f of z. So let's see. Let's write f. Usually we have an open set in the complex plane, and we're mapping into the complex numbers. Then we write f of z and say that f of z is complex differentiable. I'll write c diff for complex differentiable at a point a and c, or let's do it in omega, if the limit as z tends to a of the difference quotient f of z minus f of a over z minus a exists. If it does exist, call the limit f prime of a. Yeah, f prime of a. Okay, let me do a quick example. It's going to feel exactly like, let's do f of z equals z squared. This is going to feel like freshman calculus all over again, and it really is. So if I take the different, I'll call that difference quotient, that would be z squared minus a squared over z minus a. And that z squared minus a squared, like in freshman calculus, factors into z minus a to z plus a. And we say, aha, the z minus a's cancel, and that thing that's going to 0 in the denominator, as z tends to a, goes away. And that's, so I get here z plus a. And of course, as z tends to a, that tends to a plus a. As z tends to a. So in fact, if you start doing calculus with complex numbers, in the very beginning at least, it feels just like freshman calculus. And so it's a fact. Let's see, here's a fact. I mean, you look at, so here's a fact. All the freshman calculus facts about derivatives of a product and a quotient, etc., all go through with exactly the same proof. So they all hold true with the same proofs in the complex version. And the reason it's the same proofs is because even though the symbols mean something different, we have the same basic facts. So they all, with the same proofs, when you start talking about complex valued functions of a complex variable. And that's the reason, even though, so here's the reason. For example, the limit as z tends to a of an f of z equals L means, given an epsilon bigger than 0, there is a delta such that so in the real case, this is the absolute value. In the complex case, that's the modulus of a complex number. Okay, so such that that is less than epsilon when the modulus of z minus a is less than delta. And of course, z should be unequal to a. And so in R, this is the absolute value. In C, that thing is the modulus. And the triangle inequality is true for complex numbers, which means all the things you do, all the steps in a proof about calculus, hold in complex using exactly the same steps. So the key, triangle inequality, holds for complex numbers. It holds with the modulus of with modulus. And so the modulus of z plus w is less than or equal to the modulus of z plus the modulus of w. And so all those proofs, even though the symbols mean something different, the steps all are valid. So you can prove all the basic facts. For example, product rule, quotient rule. And you can show, so the product rule, quotient rule, etc., hold in C. So, for example, we start with 1 is complex differentiable. So C differentiable functions. 1 is complex differentiable. Z is complex differentiable. I just showed you that z squared is complex differentiable. You can start taking products. So the product of these two is z cubed, etc. So z cubed, and then you can start going back and take more products, etc. Those are all differentiable. And therefore linear combinations of them would be too, because you can see that's a linear operator pretty easily. So polynomials are complex differentiable, just like you showed in freshman calculus. And that, so consequently, we know the product rule, quotient rule. So rational functions are so let's see, a rational function would be the quotient of polynomials so these two things are polynomials. And that rational function is C differentiable, where the denominator is not 0. Where Q of Z is unequal to 0. Just like in the real case. Okay. Well, for a long time, for a couple, like a week worth of lectures, complex analysis class like Math 425 feels like freshman calculus. The first time something exciting new happens is when we come to the famous Cauchy-Riemann equations. if I write f of x plus iy is u of xy, v of xy, plus iv of xy, then the fact is, if f is complex differentiable, f complex differentiable at, let's write z naught equals x naught plus I y naught, then those u's and v's have to satisfy a special relationship. This is the Cauchy-Riemann equations. du dx has to be equal to dv dy, and du dy has to be equal to minus dv dx. That's a system of partial differential equations known as the Cauchy-Riemann equations. Okay. Well, a key thing now is I'm going to start messing around trying to prove the fundamental theorem of algebra. Let's suppose a complex polynomial p of z of degree n bigger than or equal to 1 has no zeros. Then 1 over p of z would be complex differentiable on the whole complex plane. And in fact, it would be complex differentiable over and over again. Then 1 over p of z would be C differentiable on the whole complex plane any number of times. I could do it again and again. I could take the derivative of the derivative. Okay, if I write, I claim that's going to mean that the real and imaginary parts of 1 over p of z are harmonic functions. Okay, I want to tell you why the Cauchy-Riemann equations are true before I continue here. Why the Cauchy-Riemann equations are true. I take a z naught and the complex derivative exists means that I can, when I slide in my point z, coming in any old way. So I would have f of z minus f of z naught over z minus z naught would tend to a limit, which would be that would be the f prime of z naught. And I could do it along any direction. It would have to go to the same thing. Well, the Cauchy-Riemann equations we observe, instead of sliding in along arbitrary directions, I slide in along two directions. One direction is going to be the horizontal direction. So I'm going to let z slide in to z naught along the horizontal direction. And then I'm going to let z slide into z naught from the vertical direction. And those would have to be the same. Those limits would both have to go to L. Okay? The horizontal direction slide shows, when you write out the difference quotient and look at it, it shows that f prime of z naught is equal to du dx at x naught y naught plus I times dv dx at x naught y naught. I like to call that red box number 1. And that's what you get when you slide in horizontally. And the vertical slide has a funny thing in the denominator. You have an I times something in the denominator. And when you do the algebra and write it out, the vertical slide looks like it's going to give you something different. The vertical slide shows f prime of z naught is equal to du dx is equal to dv dy x naught y naught minus I times du dy. Okay, red box number 1 is extremely straightforward to get. I'll show you red box number 2. Okay, when you equate the red boxes, you get the Cauchy-Riemann equations by equating the real and imaginary parts. Okay, that's how you do it. Let me show you the red box number 2. If I'm sliding in along the vertical direction, so here's z naught equals x naught plus I y naught. And so this z sliding in along the vertical direction would be z equals x naught would be the same, but I'd have an IY. And so when I calculate the difference quotient, let's see, the difference quotient would be, I'd have z minus z naught over f of z minus f of z naught. That would, f of z would be f, I'm going to write it in terms of u's and v's now. U of x naught y plus IV of x naught y minus the same thing at x naught y naughts. And on the bottom, I'd have, subtracting those two things, the x naughts would cancel, and on the bottom I would get I times y minus y naught. Then when I collect terms and distribute that I through there, let's see, the one where the v terms, the i's are going to cancel. And I'll put those v terms right away here. That would give me v of x naught y minus v of x naught y naught divided by y minus y naught. And sure enough, that's going to, as I let y slide in, that's going to show me that that partial derivative exists and it's the real part of that thing. And then the imaginary part, let's see, I'll get a 1 over I. And 1 over I is minus I. That's the 1 over I thing. And then the rest of the stuff is the u stuff. And so I get 1 over I, minus I times the difference quotient for the u partial derivative with respect to y. So sure enough, as I slide in, those things are converging to partial derivatives, which have to be that same limit L. So that's how that works. It's not hard. So it's sort of an elementary thing. But a fascinating thing I can do, if I do the Cauchy-Riemann equations, so here's a big fact. If f of z is differentiable, and f prime of z is 2. It's a funny fact that if f is complex differentiable, it automatically happens that f prime is c differentiable too. But we have this situation, so we don't have to think about it. If that is 2, then when I write f of x plus iy is these two, the sum of two things, these two functions turn out to be harmonic. Then the real and imaginary parts, u and v, are harmonic. And therefore, they're going to satisfy the averaging property. That's exciting. So it's a corollary. It's a fact, I should say. Real and imaginary parts of analytic functions are harmonic. So analytic meaning complex differentiable on an open set. And that's one reason complex analysis is so important. Harmonic functions are everywhere in science and engineering and math. And in fact, the reverse is kind of true. If you give me any old harmonic function, well, it's actually locally the real part of an analytic function. So you got to study complex differentiable functions if you're going to understand harmonic functions. Okay, so let's see why this is true. Let's see. So I would have f equals u plus iv. I had red box number 1. So red box number 1. Which was that f prime was equal to du dx plus I dv dx. Okay. And red box number 2 gave me another way to write f prime. F prime equals du dy minus I dv dy. Well, however I write those two things, I'm going to write them now as capital U plus I times capital V. Capital U and capital V satisfy the Cauchy-Riemann equations. If I can differentiate it more than once. And that's going to show me that they're harmonic. Okay, so let's think about let me write out the Cauchy-Riemann equations then. So let's see. d by dx, I'm going to put here du by dx. Du by dx is capital U. That would be equal to d by dy of v. And v, what is dv? What do I want to put for v here? dv. What?
I think we want minus partial v.
Oh yeah, what the heck? I know the Cauchy-Riemann equations. Let's see, du dx is dv dy. dv dx is minus du dy. Thank you. Let's see. So now, v is dv dx. What am I doing? That's true. Okay, and now I'm going to have that's equal to d by dx of the other u I'm going to write the u again, but this time I'm going to write it as the other one, dv dy. And that's equal to d by dy of the v, which this time I'm going to write it as minus du dy. Let's see, so which one of these is going to give me the... there it is. When I put these two together, this one and this one, this shows me that du dx dx equals minus du dy dy. That's the Laplace equation. Laplacian of u is equal to du dx dx plus du dy dy, and we see that that's 0. That shows that u is harmonic. And similar work would show that v is harmonic. Let's see, where's the v one? I'd have to do it again for the other one. And so I would repeat it for the, I'm not going to dwell on this, repeat for the other Cauchy-Riemann equation. Repeat for the d by dy part. Let's see, that would be d by dy, let me write it out fast, of du by dx. That's one way to write the u. I want it for little v, to see little v is harmonic. And I don't get it from that top one. That just, those are the mixed partial derivatives being equal. So I have to do it again for the second one. And when I do it this time, I would get minus d by dx of v and v is dv by dx. And that's d by dy, the other Cauchy-Riemann equation of u, which this time is dv by dy. And there's the one I need. And this, the final one is minus du dx of v, which is minus du dy. So what do I need? Yes, I see it now. This one. That's going to give me minus dv dx dx. Anyway, it's just doing the Cauchy-Riemann equations twice. And that's a minus, so that would be plus. Where's my v? No, not that one. This one. That's dv dx plus dv dy dy. These are equal. So that gives me the Laplacian of v is 0, too. So the real and imaginary parts are harmonic. Okay, that's an exciting thing. So why is this going to be great for us? I'm going to prove the fundamental theorem of algebra using this fact. I'll write 1 over my polynomial, which has no zeros, on the complex plane. It's infinitely complex differentiable, so that's going to be equal to u plus iv, where these u's and v's satisfy the Laplace equation. They're harmonic. So we know now that the u and the v are harmonic. Harmonic functions satisfy the averaging property. That's something we showed using Green's theorem. Well, it turns out that polynomials grow as z goes out far away along big circles, like z to the n, in fact. And so 1 over p of z shrinks. So the key here is that 1 over p at 0, p is non-vanishing, so this is p of 0 is not 0, and this thing is not 0. That's going to be the average. So that would be 1 over 2 pi, and we'd integrate from 0 to 2 pi, and we take the average of these things on a big circle. So that would be u of r cosine theta, r sine theta, plus the imaginary part of v of r cosine theta, r sine theta, d theta. That just means take the real and imaginary part of that and calculate those integrals. This goes to 0 as r goes to infinity, because polynomials get bigger and bigger, and so when you take 1 over them, they get smaller and smaller. And that's a contradiction. So it can't be the case that p has no zeros, because then I get this contradiction. That's what I needed to be able to get the harmonic functions and use the averaging property. Okay, so that's how it's going to go. And so how do I show that polynomials blow up for big Z? It's easy. So the little lemma. Let me get rid of this first coefficient. Since an is not 0, that means it's degree n. So I'll start with a z being 1 here. Yeah, let's do that. I'll leave the... Okay, a1z plus a0. I can factor out the z to the n. So I get z to the n times an plus, let's see, this would be an minus 1 over z plus, then we get a1 over z to the n minus 1 plus a naught over z to the n. These all tend to 0 as z gets gigantic. So let's call this h of z. H of z goes to 0 as the modulus of z goes off to infinity. Because I'm dividing by those things which are gigantic. And so this means that we can, if you think of, here's 0, here's an is not 0. And so if I want to keep that thing in the parentheses away from 0, I just have to pick n big enough, z big enough in modulus, so the picture looks like this. I'll take a little disk like this. Let's call this radius epsilon. So there would exist an r bigger than 0 such that h of z is less than, let's let that epsilon be equal to an over 2. I'm taking epsilon like in the picture here, the modulus of an over 2. When the modulus of z is bigger than r. Okay, so let's see, the h of z then would be an, this is my, where's my, an plus h of z would be someplace in here. If the h of z is less than that radius. And so I see that my polynomial, I would get, let's see, how my polynomial then is bigger. This is the basic polynomial estimate. I would get that a times z to the n is less than or equal to the modulus of my polynomial is less than or equal to something times z to the n when the modulus of z is bigger than r. Okay, so what's the a? The a in this picture would be an over 2. And the b in this picture would be 3an over 2. But what that shows is that the polynomial gets gigantic as when z is far out there. And so 1 over p of z, I'm going to get 1 over p of z, would be less than or equal to 1 over b times z to the n. And that'd be less than or equal to 1 over a times z to the n. And this inequality is the one that shows that it's shrinking very fast at infinity. This shows that 1 over p of z is going to 0 very fast, like z to the n, as the modulus of z goes to infinity. Okay, so eventually it's really small, and if you take the average of something that's really small, like if it's always less than 0 degrees, your average temperature is going to be less than or equal to 0 degrees. So if it's getting really small out there and you take the average, you get something really small. So the average of a really small function is really small. Okay. But that average among gigantic circles has to be the value at 0. And that's where the contradiction comes from. Any questions about any of that? So that's sort of the quickest proof of the fundamental theorem of algebra I could come up with, based on what we know. We know the averaging property because we used Green's theorem to get it, if you look back in a previous lecture. Yeah. Did I explain this enough? It's kind of a picture proof. My an plus h of z is stuck between this smaller circle here and this bigger circle here. That's where I get the an over 2 is the smaller bound, and the 3an over 2 is the bigger bound. So this radius is my capital A, and this radius is my capital B. Okay, well that's enough for today. So I'll see you on Monday. The video lecture on Friday is about the vibrating square drum head. There were some fun things I didn't tell you about it before, so it's worth looking at, I think. If you take Math 425, I'll do this very carefully, and it follows from Liouville's theorem in that course, which is also quick and easy, but it takes longer to explain.
There's no in-person lecture on Friday?
No. Yeah, so I won't be here on Friday. I sent an email about that. Did you get that?
You sent it today?
No, I sent it yesterday. Anyway, I explained what's happening in my email.
I think I might have missed it. I don't think I got it.
Really? That's weird.
Yeah, the last one I had from you was from the 1st of April.
That's weird.
Maybe.
What the heck?
Some error.
I hope not. Maybe I should send it again. I sent it in bright space.